Welcome to the Explainer. Today, we're cracking the case of the boiling bubbles. You know the drill, right? You put a pot of water on the stove, turn up the heat, and pretty soon you see all those bubbles rising to the top. But what's actually happening there? What exactly is inside those bubbles? Well, let's put on our detective hats and follow the evidence to figure it out. So here's the absolutely crucial question. When water boils, do those bubbles contain a brand new substance? I mean, it's super tempting to look at a rolling boil and just assume, oh, that's just air, or maybe think it's some entirely new gas created by a chemical reaction. We see the bubbles, we watch them pop, but here's the thing. In science, looking just isn't enough. We can't completely trust our eyes. We need hard data. We need mathematical proof to really unmask the culprit here. So to figure out what's actually inside, we're going to need to capture that gas and put it through its paces. All right, so to test it, we set up a little investigation. Picture this. We put some water in a flask, set it on a hot plate, and seal the top with a cork that's hooked up to some tubing. As the water starts to boil, that mystery gas is forced up and right out through the tube. Now, one of the quickest ways to ID a gas is to test its flammability, right? So we capture what's coming out of the tube and hold a lit match right up to it. If this gas was highly reactive, whoa, we'd see a massive flare-up. But that doesn't happen. Instead, the very second the flame gets near our mystery gas, it goes out, instantly. Because our gas just completely snuffed out the match, we can go ahead and cross some major suspects right off our list. Hydrogen? Nope, that would have given us a pretty serious pop. Methane, propane? Definitely not. Those are highly flammable fuels. Even oxygen is totally off the table here, because extra oxygen would have made that flame burn way brighter, not die out. So whatever this gas is, we know for sure it is decidedly not flammable. Okay, so we've got our first solid piece of evidence. But it's still not quite enough for a positive ID. We gotta look a little closer. So we keep the hot plate running, but this time we feed the end of our tubing into a second unheated flask. And as that hot gas travels away from the heat, something really fascinating happens. It cools down, and we actually start to see these little droplets forming on the inside of the new glass. The gas is condensing back into a liquid. And not just any liquid, but a perfectly clear liquid. Now, I know what you're probably thinking. You're thinking, well, obviously, it's just water. But hey, remember our golden rule? We absolutely cannot trust our eyes alone. Because honestly, just because it looks like water doesn't mean it actually is. The scientific world is literally full of clear liquids that are entirely different substances. Think about rubbing alcohol or glycerin. These are completely different chemicals. You probably have them sitting in your house right now. Actually, both of those are super common in homemade bath bomb recipes. And guess what? They're all clear and they're all liquid at room temperature. If we just rely on what things look like, we're completely stuck. To definitively prove what's sitting in that second flask, we need to find a property that's entirely unique to each specific substance. And to figure that out, we get to pull out our ultimate investigative tool, density. You can kind of think of density as this mathematical fingerprint for matter. It is determined as a ratio of mass to volume, which gives us a unit rate. And here's what makes density so incredibly powerful. It is a constant property for any sample of a substance, completely regardless of size. Seriously, whether you have a tiny microscopic drop of a liquid or enough of it to fill an entire swimming pool, the ratio of its mass to its volume will always stay exactly the same. So if we can just figure out the density of our mystery liquid, we can crack this case wide open. But to find that mathematical fingerprint, we need some really precise data. So here's what we do. First, we weigh an empty 25 milliliter cylinder. Then, we pour in our clear mystery liquid and weigh it a second time to find its exact mass in grams. Finally, we check the volume. You got to get right down at eye level and read it at the lowest point of that little curve at the top of the liquid, the meniscus. It's a pretty simple procedure, but it gives us the exact mass and volume data we need to move forward. Okay, so once we collect mass and volume data for a bunch of different sample sizes, we can plot the whole thing out on a coordinate graph. Let's start by looking at the baseline data for known pure water. Check out how these data points form this beautifully straight line that shoots right through the origin, straight through 0, 0. That is a total aha moment right there in the data. It proves that mass and volume have a directly proportional relationship. Basically, every single time you add a milliliter of water, the mass goes up by a totally predictable, constant amount. And for water, that unit rate is about 1 extra gram for every 1 milliliter. Now, let's contrast that with one of our sneaky clear liquid lookalikes, glycerin.
Just look at the steepness of this line. The graph is telling us a completely different story here. Glycerin actually packs significantly more mass into every single milliliter than water does. Because its unit rate is higher, its plot just climbs up that y-axis way faster. To put that into perspective, if you poured the exact same volume of glycerin and water into two identical cups, the cup holding the glycerin would feel noticeably heavier in your hands. And then we have the plot for rubbing alcohol. Look really closely at the angle of this line compared to the others we just saw. It's actually the least steep of all three. That flatter trajectory is visual proof that rubbing alcohol has less mass for every milliliter of space it takes up, so it's the least dense of our three clear suspects. By plotting these graphs side by side like this, it's like magic. We can visually and mathematically separate three totally identical-looking liquids based purely on their physical properties. So when we bring all of this calculated data together to lock in our baselines, the math gives us these averages. Water clocks in right around 1.0 grams per milliliter. Rubbing alcohol is the lighter one, sitting at roughly 0.78 grams per milliliter. And glycerin is the heavy hitter, coming in at about 1.26 grams per milliliter. These numbers right here, these are their unique, undeniable fingerprints. All right, the moment of truth has finally arrived. We take that unknown, mysterious, clear liquid that condensed over in our second flask, the liquid that came from the gas inside those boiling bubbles, and we run it through the exact same procedure. We weigh it, we get down and read the meniscus to find the volume, and then we divide the mass by the volume. And, drumroll please, the final verdict? It clocks in at exactly 1.0 grams per milliliter. It is a perfect match for the mathematical fingerprint of pure water. Which brings us to a definitive, rock-solid scientific conclusion, straight from our evidence. The gas produced by the heated water is made of the exact same type of particles as those in the water that we started with. We absolutely didn't create a new substance here. All the heat did was give the water molecules enough energy to spread apart and become a gas. Boiling is quite literally just a phase change. Those bubbles, they aren't made of air, and they definitely aren't some newly formed chemical. They're just water vapor. The particles themselves never changed at all. So there we have it. We've officially solved the case of the boiling bubbles. We know for sure that heating water simply shifts it from a liquid phase to a gas phase without creating a new substance. But, man, it leaves us with a truly fascinating new question to ponder. If adding heat energy just separates the molecules, what on earth happens if we pump a completely different type of energy into the water? Like, what happens if we blast it with electricity instead? Will it still just be water vapor, or will we finally break the water apart into something entirely new? Keep that question brewing in the back of your mind as you continue your scientific journey. Thanks so much for joining me on this explainer, and as always, stay curious.